Okay, I guess you can hear me well now. Thanks for the introduction again. And yes, I'm on the job market now since I just defended 3 days ago. So, and I'm John. I'm still officially a PhD student at ETH Zurich and a lecturer at ETH Zurich as well. And today I'll talk about a particular direction that was a bit maybe different than the previous talks. So I'll present Rawsamble, overlapping and assembling raw nanopore signals using a hash-based seeding mechanism. So I'll start with an executive summary. So we know that there are many recent works that aim to map raw nanopore signals to reference genomes without base calling them. But we also find that the existing solutions cannot really interpret or analyze raw signals directly, for example, for reference-free applications or if the reference genome is unknown. So our goal is to enable raw signal analysis without a reference genome. To this end, we make 3 key contributions. First, we propose Rawsamble, which is the first mechanism that can find overlapping pairs between raw nanopore signals without base calling. Second, we built the first de novo assemblies ever constructed directly from raw signal overlaps without base calling again. We also designed a new assembler to build and output the assemblies of signals. Across different genomes of varying sizes, we show that Rawsamble, our work, provides an average speedup of 16 times compared to the configuration where we first used Dorado's first fast model for base calling, followed by Minimap2 to find overlaps. When we also look at the overlapping statistics, we find that 37% of the overlapping pairs that Rawsamble finds are shared with the Minimap2 overlaps. And when we construct assemblies from these overlaps using Rawsamble, we find that the unitics we construct are 400 times longer than the average read length. So I'll start with a quick background. So as we probably all know, nanopore sequencing is a widely used sequencing technology. So it can sequence large fragments of nucleic acid molecules up to 4 million bases. It offers high throughput, it is relatively cost effective, and it also enables these unique features such as real-time and portable analysis. So this is a nanopore sequencer. It contains many tiny pores that we call nanopores. And as the nucleic acid molecule passes through the single nanopore from the negatively charged side to the positively charged side, we can measure the ionic current disruptions as raw electrical signals at a certain throughput. And we can analyze these raw signals actually instantly as they are generated, which we refer to as real-time analysis. And we can even make real-time decisions to stop the sequencing early and also even the entire sequencing run based on this real-time analysis. So there are 2 main ways of analyzing raw nanopore signals. The first one is the traditional way is to translate these raw signals or base call them to base called sequences and followed by the regular downstream analysis tools such as read mapping. So this approach is less noisy, so it's more accurate analysis. And we all know that there are many analysis tools that use these base called sequences. However, especially for base calling, these tools require use complex deep neural models and require the use of power-hungry devices such as GPUs. There are also some recent works that aim to directly analyze raw signals without base calling by mapping them to reference genomes. So these approaches provide efficient analysis with better scalability and portability. And also we know that raw signals retain more information than just individual bases. But we also know that there is this lack of established tools that can perform raw signal analysis without base calling in the downstream analysis. So let's see how we can map raw signals to reference genomes without base calling them by looking at the state-of-the-art raw signal mapper RowHash and RowHash2. So it typically starts by converting the reference genome into its electrical signal representation by using the somewhat conversion table that takes each chimer of a reference genome as input and then outputs its expected electrical signal. So now we have this the synthetic reference signal that we call from the reference genome and also raw nanopore signal, and then we somehow generate hash values from these signals and then perform the regular hash-based seeding and mapping steps. So the synthetic signals that we're using for the reference genome are mainly noise-free. They don't necessarily contain the errors that nanopore sequencing contains. But in order for you to perform this analysis, you need to have a reference genome to perform the mapping. So we find that the existing solutions cannot analyze raw signals directly without a reference genome. So if you really if you want to go beyond the reference mapping, what you can do is overlapping. Because, for example, the reference genomes may not be available, or you may want to perform reference-free analysis. Then what you can do, we could construct the genome itself to build the assembly from these overlapping reads, but we cannot really do this without base calling. Because there are essentially certain challenges to it. So the first challenge is now instead of essentially dealing with one pair of noisy raw signal, now we have two noisy signals that we need to map to each other. The second is now we need to find many useful overlapping pairs that we call all versus all overlapping pairs from these noisy signals. And also we need to generate long paths from these useful overlaps so that we can construct the assembly. Now I'll describe our mechanism Rawsamble. So our goal is to enable raw signal analysis without a reference genome. To this end, we propose Rawsamble. We make three key contributions. We propose the first mechanism that can perform all versus all overlapping from raw signals. We built the first de novo assemblies ever constructed from raw signals. And we design a new assembler to build and output the assemblies from raw signals again. Rawsamble has two high-level basic key ideas. We built on the existing state-of-the-art raw signal mapper, RowHash2, and then we extend RowHash2 to support the overlapping. So in order to explain how we essentially extend on RowHash2, I'll quickly show you how RowHash2 works to perform the raw signal mapping to a reference genome. So as it so happens with any read mapper, it has two steps, the indexing and mapping. And in both steps, we apply a quantization on the signal so that we can reduce the noise a bit. Then we generate hash values from these signals, and we can also even perform some sketching, for example, minimizer sketching. And based on the hash values we generate from the reference genome, we store these hash values in the index, and then also query the hash values we generate from raw signals so that we can find matching regions from the reference genome and also the raw signals. And it essentially is followed by the regular filtering and the chaining steps so that we can find the mapping positions, the best mapping position for that particular raw signal. So this is basically how the RowHash2 works. So we make four key changes on it so that we can output the overlapping pairs. The first, now instead of storing the reference signals, we store the raw nanopore signals directly in the index. Second, we apply a filtering so that we can reduce the noise that we store in the index. Third, we modify the chaining and also the outputting strategy so that we can report all versus all overlapping pairs, which can be used by the off-the-shelf assemblers directly to build de novo assemblies. So when we construct the index from raw signals, this means that we're no longer constructing the index from reference genome, which is mainly free from noise. Rather, we're essentially now storing the noisy raw signals in the index. So in order to reduce this noise that we're storing in the index, we apply an aggressive filtering, which essentially removes the consecutive signals that are similar to each other aggressively. So this is one example over here. For example, these three signals can be close to each other in terms of the value, but we only keep one of them. So this essentially, in high level, it removes some errors that we know as stay errors in nanopore sequencing. So we also make some changes in the chaining strategy that we use in RowHash2. So what we find is that when we perform overlapping, we find a large number of chains basically between read pairs. So in order to identify the highly accurate chains, so we increase the chaining score up to around 5 times so that we can find the reliable ones. And then by doing so, we report all chains as all versus all overlapping pairs. We also need to avoid cyclic overlaps. So these raw signals can map to each other cyclically. So when using, for example, the target signal as query and vice versa due to some shared regions. So to prevent cyclic overlaps, we perform some simple deterministic comparison and report each overlapping pair only once. So this covers all of the optimizations that we propose in Rawsamble to identify the all versus all overlaps. So now I'm going to cover the evaluation methodology. So we integrate Rawsamble into RowHash2. and we compare the overlaps that we find using Rawsamble to the overlaps that Minimap2 finds on the forward strand. We use Dorado's various models, like fast model and also the high accuracy and super high accuracy model using CPUs and GPUs. We evaluate the overlaps that we generate using a particular use case. Here in this case, we construct de novo assemblies from the overlaps using Miniasm off the shelf without even changing the Miniasm. But we also discuss some new exciting directions as future work in the later slides. We evaluate these tools in terms of the runtime and also the percentage of shared overlaps between tools, and we build assemblies and then we report some assembly statistics. We use 5 real data sets with various coverages from even less than a sequencing depth of coverage up to around 450x, and also with various genome lengths. So I'll first show the normalized run times. So this figure shows on the y-axis the runtimes normalized to Rawsamble's runtime, and also on the x-axis we have different data sets. Here we also show the particular configurations on the top. For example, when we have Minimap2 plus Dorado CPU, this means that we first base call the raw signals using Dorado's fast model using CPU, then we use Minimap2 to find the overlaps. First, we find that compared to the fastest CPU model using Dorado, Rawsamble provides an average speed up of around 16x. And second, Rawsamble provides an average speed up of 2 times compared to the configuration when using Dorado's conventional GPU model. So these are essentially the runtime results. So next, we look at the all versus all overlapping statistics in terms of the percentage of overlapping pairs that are shared between tools, and also unique to Rawsamble and unique to Minimap2. And this Venn diagram essentially shows these percentages. So what we find is essentially around 37% of the overlapping pairs are shared with the Minimap2 overlaps. But the question is, so how do we evaluate these usefulness of these overlaps? In order to evaluate this, we essentially build de novo assemblies from the overlaps, but I'll mainly focus on 2 assemblies, one from E. coli and the second one from the human genome. So here this figure shows the visualization of the assembly graph. We construct the raw signal overlap. So the biggest takeaway is that we can now essentially construct de novo assemblies from the raw signals without base calling them. And these assemblies, these contigs are not necessarily short. For example, we can construct a contig of the half the E. coli genome length, which is essentially 400 times longer than the average read length for that particular data set. So, for example, for the future work, we can think of utilizing the overlap and the assembly information when training and using base callers. Now we also look at this radar chart that we essentially show on a human genome that we construct using a low coverage read set. Here we have 3 metrics, ON, longest unitic, and the largest component. Essentially what we find here is that, especially for low coverage data set, Rawsamble leads to better contiguity than using base called reads at a low coverage data set. So the question is essentially, can the richer information in raw signals improve the assembly quality where base called analysis may fall short? So we essentially identify at least three key future research directions. First, now we can construct and also analyze de novo assemblies directly from raw signals without base calling them, which we already do in this work. But second, now we essentially have this overlap information that we are generating from Rawsamble. And in the regular case, what we have is we input these raw signals into base callers and then base call them. So rather, what we could do, we could also generate the overlap information between raw signals and also input these overlap information to base callers, which can be used as essentially as additional feature to improve the accuracy and even maybe the performance of base callers. So third, similar to the second one, we can also utilize the constructed assembly for base calling. So for example, we build the assemblies from overlaps. We could also perform maybe error correction on the assembly. And then instead of base calling each raw signal once, we could directly base call the assembled signal only once. So Rawsamble is available on archive as preprint. So you can essentially reach to the preprint using these QR codes, and also the source code is fully available. We also have a de novo assembler that takes the raw signal overlaps as input and outputs the assemblies from raw signals. So this is slightly modified version of Miniasm. So it supports all major raw signal file formats. And this is still in a testing phase, so feedback is appreciated. So with that, I'll conclude. We make 3 key contributions. Rawsamble that finds the overlapping pairs. We construct the first ever de novo assemblies ever constructed from raw signal overlaps without base calling, and we design a new assembler. We show that we can improve the performance and also accuracy from these overlaps. And we believe that there are many opportunities for analyzing raw signals exist. For example, we should rethink the base calling approaches by integrating the raw signal analysis information. So with that, I'll conclude my talk and happy to take questions.